Can everybody hear me? Thumbs up? Right. Okay, so good afternoon, everybody. I'm really sorry I can't be with you in person. My name's Rob. I'm in charge of the Advanced Computing Programme at the UK Atomic Energy Authority. So Peter Coveney asked me if I could say a few words about where we are in terms of our UQ journey for fusion. So I thought I'd perhaps start by saying what fusion is, in case there's anybody in the room who hasn't seen us in the news over the last few years. So fusion is the process that powers the sun and the stars. It's almost the most fundamental way that the universe makes energy. And it does so inside a star through this rather complicated process here on the left. So the sun is a neutron factory, effectively, and that's a very slow process. It's a so-called electroweak process that involves making neutrinos that you may have heard of. Unfortunately, it means that a given cubic meter of the sun only makes a small handful of light bulbs worth of energy. It's a very, very slow process and only works for the sun because, of course, it's so large. Now, if we wanted to replicate the fusion process in the laboratory, we can't use the solar fusion life cycle. We have to use this process here on the right, which is where we take deuterium and tritium, and rather than gravitationally confining it, we contain it inside a magnetic bottle. We use magnetic fields in something called a tokamak. Now, we've been doing this for many years. The UK Atomic Energy Authority has its operations mainly based at Culham Centre for Fusion Energy in Oxfordshire. And we, in fact, curate the world's largest magnetic confinement fusion experiment called JET. It's been operating for 4 decades up here on the left. But we also have many other new facilities that have started springing up over the last 5 years or so. I haven't got time to go into them in any great detail. But the reason for this is that we're on the cusp of commercialization now. We're actually moving from the science domain into the commercial engineering domain of fusion. And upright in the top of this diagram is a new part to our program, and that is that we now have a proper advanced computing initiative at UKEA that is growing incredibly fast. We're doubling year upon year. And this is because we've been set a grand challenge by the government. So perhaps crystallized to some extent due to Brexit, the UK has now decided that it's going to undergo its own initiative in fusion in addition to the ITER experiment that we're part of in the south of France. And we're going to have a go at putting power onto the grid in the 2040s. So that means we've got a couple of decades in which to design and construct a fusion reactor that will do what the sun does, but at a much smaller scale, but still sufficient to produce hundreds of megawatts, if not gigawatts of power, as a baseload carbon-free energy source. What is the challenge, though, around this? So we've got 2 decades in which to do it. Well, the problem really is that we're at the bottom of the engineering S-curve. So all products that go from concept through to maturity, through to marketability, tend to follow a curve that looks like this. So you can think of performance on the y-axis here as product readiness or marketability of the product, market uptake, and then time along the bottom. And we start from pioneering science and overcoming some of the major obstacles with our concept. And then we have to climb through this very steep part of the curve as we sustain mastery over the technology, if you like, until we then get into this flat top region at the top, which is where the product becomes commercially viable. Now, the problem with this is all of engineering in the modern world is used to working at the top of the S-curve. You know, if you think of anything that big in engineering that's happened in the last 50 years, it was quite a few decades ago. So, you know, we put man on the moon in the late 60s and 70s, and that's when NASA climbed the engineering S-curve through this steep region. And now Elon Musk is working at the top of the S-curve. So how did NASA do that? Well, it did so through test-based design. And that's, in fact, exactly what Elon Musk is doing today. So we're used to doing this in engineering. We're used to iterating and using experiential evidence in order to move forwards. We're not used to doing everything through simulation and modeling. Unfortunately, having 20 years to do this in Fusion, we have no more time now to build another tokamak that sits between jet and the reactor scales. So we have a very steep curve to climb. And this means we need a paradigm shift in how actionable our simulation capability is. So that's the mission of the Advanced Computing Program at UKA, is to try and accelerate the delivery of commercial fusion energy by exploiting advances in data science and extreme scale computing. And I'm now going to go on and say a few words about what I consider to be the major challenges of engineering in silico, if you like, going forwards. So number one, we need to validate our models much better than we've been used to. Instead of trying to spend all of our time confirming that our models work, in fact, we need to start devalidating our models. And in order to do so, we obviously need UQ moving forwards. The simulation challenges themselves, rather annoyingly, a so-called exascale grand challenge. We need the most powerful computers in the world to do predictive modeling. I'll then say a few words about so-called black swans, which are problematic for engineering simulation-based prediction, less so perhaps for the science. The science tends to hunt out the black swans. In engineering, of course, we want to avoid them. I'll then say a few words about the fact we need better UQ solutions, and then finally a few words about where the UQ comes in through human error. So we'd love to be able to take a data-centric engineering approach to fusion engineering design. And in fact, we do have a lot of data, and these are many of the tokamaks that sit around the world or are being built. And of course, there are many, many more. The problem is the data tends to sit within silos, within all of these different laboratories spread around the planet. And to date, we've not been very good at sharing our data. So our data is very hard to wrangle together to take a data-centric engineering approach. We've got to fix this, yeah? So it's a big data challenge, but it's also a big sparse data problem as well, in that the fusion engineering design space is a very high dimensional space. But nevertheless, we still need to do what is espoused at the Alan Turing Institute and try as much as possible to take a data-centric engineering approach to try and make sure that engineering is based upon all prior data, all prior knowledge. The challenge with this, though, is we've got to get much, much better at sharing our data. So on this journey, we've set out through a European-funded project called Fair for Fusion to try and make our data more findable, accessible, interoperable, and reusable. And you can see a link to the project here at the bottom, plus a paper by David Costa that kind of outlines the plan. This is essential going forward. We've got to get much better at basing all decisions upon all prior data. Now, the good news is this isn't unique to Fusion. And I know this because I brush shoulders with many others solving very similar challenges. And here, in fact, is a flow chart that if you'd put in front of me a year or so ago as a proposal for data sharing in the Fusion domain, I'd have looked at it and I wouldn't have batted an eyelid. It looks quite familiar. This, though, is a workflow. It's a so-called fair data pipeline that's being developed through the Scottish COVID Response Consortium that UKA joined to help with through our RSE initiative as part of the RAMP initiative. So we are sharing this problem. We're trying to solve the same problem as the epidemiologists. In terms of scaling out our fair data systems, though, I think we're taking a slightly different approach. We're going to look a lot more at the out-of-the-box solutions. So we have a nice project here that we're doing with the University of Manchester that is asking the question, can we actually design fusion reactors in the metaverse? So I'm sure many people in the room have heard about the metaverse, and it's probably at the peak of the Gartner hype curve at the moment. But interestingly, NVIDIA has a very interesting solution here with a platform they're calling Omniverse, which is solving many of the challenges that I think we need to tackle in order to make our data more accessible and to connect people, processes, and tools a lot more efficiently in the information era. So if anybody's interested in learning more about where this project goes, I'd be very keen to share what our findings and maybe even to potentially collaborate on seeing whether the metaverse can also be used as a platform for the other areas of science and engineering. So, for example, for pandemic modeling. The next challenge is simulation itself. So this shows a couple of graphs kind of demonstrating the complexity of the problem in terms of fusion simulation. So we've long been heralded a grand challenge problem, a so-called exascale grand challenge problem in both the plasma and the materials simulations. And that's because these span many decades in both temporal and spatial scale lengths. And those scale lengths tend to be coupled. So in the plasma physics, we go right the way from the physics down at the gyro motion of the particles inside the plasma, right the way through to magnetohydrodynamics and the gross instabilities we get inside the plasma. And then in the materials, we have to span going from electronic structure through atomistic modeling through to microstructure and then up to the macro scale, where we want to be able to model component behavior at scale inside reactor digital twins. So this is a real challenge from a simulation point of view. Our simulations take an awful long time to run, and we've got to get them a lot faster running at scale on the exascale supercomputers that will be appearing in the next few years, all of which, of course, have got very exotic hardware architectures under the hood. So this is a real challenge for us, the fact that we're an exascale problem. Now, it means that many of our models are model order reduced for running on existing supercomputers. And this means that our models are absolutely riddled with epistemic model uncertainty. And in fact, we really only use our models at the moment as interpretive tools on the experiments. We don't use them for engineering design. So because of those epistemics, it means that our codes don't predict well into the reactor regime. So we've got to get the epistemic model uncertainty under control. And this needs a much more detailed approach to the way we do UQ and a coordinated approach going forwards. This effectively is the essence of what we need to do. At the moment, we work in these blue areas. We work on plasma simulation, trying to get that to work at the exascale. Similarly for the materials modeling, for the density functional theory and molecular dynamics that we do. And also increasingly now, because of STEP, engineering plant simulation. These areas, though, overlap. All of these areas couple together. A reactor is a highly coupled system of systems problem. So the plasma simulation couples to the materials simulations, where the plasma meets the wall of the machine. Where the plasma touches the engineering plant simulation, effectively through the electromagnetic field inside the reactor. We need flight simulators, and not because we fly a tokamak, but we do control it in the same way that a test pilot would fly a new aircraft. We talk here about flight simulators being the systems that use us to predict operations and make sure that we can run the plasma effectively and make sure that we don't damage the machine. And then the materials simulations touch the engineering plant simulations when we want to be able to use simulation to predict that the plant isn't going to break, or for predictive maintenance for that type of thing. All of these need to be informed by a so-called digital thread, which is the knowledge and information management that I referred to on a few slides earlier. So these simulation capabilities need to be validated against reality, and this requires wrangling data from experiments around the world, from all of the simulations that we do, from all of the tacit knowledge that tends to be locked up in people's heads, from new test facilities like the ones I showed near the start of my talk that we're building at Culham, and also our new facilities in Rotherham, and from the engineering design data that our engineers are starting to produce on STEP itself. All of this is a big data challenge, and it's a big simulation challenge as we try to move in on the center of that Venn diagram to be able to build a digital twin equivalent to the STEP reactor itself. So we're going to need the world's largest supercomputers, machines like Frontier and Aurora, that are hopefully going to be available this year in the United States. And We've also got to work out how we use these machines to do UQ at scale, which I think initially is going to be through huge amounts of non-intrusive ensemble-based simulation. So why in non-intrusive ensemble-based simulation? Well, time scale, effectively. We'd love to rewrite a lot of our legacy codes. Got an awful lot of black box infrastructure that dates back decades that, we've lost a lot of knowledge around those different agents or actors within the many coupled workflows that we try to deploy. And I show one here for the European Transport Solver, which models the flow of energy particles and momentum through the plasma. If you look at Peter Coveney's diagram from the VECMA project here on the right, though, if we're at the point where we know little about the models, that does tend to force us into a non-intrusive paradigm. We treat those agents as black boxes. I think going forwards, though, with these coupled workflows, we are going to be looking at the semi-intrusive meta-modeling approaches, and we're starting to ramp up activities now around the surrogate modeling development that's needed. We're working closely with NVIDIA. We've got a new collaboration with the Hartree Centre, where we're developing new surrogate modeling techniques, and a new one, actually, that we've started spinning up with Microsoft Research Cambridge, where we're going to be having a look at whether the AI methods are useful for UQ purposes within these very complex workflows. We're also connecting to the CEVIA project. We can't spin up a team fast enough at UKEA in order to do this ourselves, and it doesn't make sense to do so. We're not UQ experts, we're fusion experts. So we're trying to bring together a rainbow team across the UK, some of the partners shown up here on the right. And fusion is embedded as a major use case within the CEVIA project. You can use the link at the bottom left to connect to this as part of the Excalibur program within which CEVIA sits. I think our emphasis at UKEA going forward is going to be around the surrogate modeling itself, working with people like Serge Guias on the multi-output Gaussian processor, but also the machine learning-based surrogate techniques. Also, I think there's a lot we need to be doing together around the emerging UQ techniques, and I'll say a few words around why that's important in a moment. This is our use case within CEVIA. Here on the right, you can see a video. Hopefully this is streaming okay. This is the MAST upgrade plasma. This is an EPSERC flagship experiment that we operate at Culham. You might have seen it on the BBC News recently. Here we're exploring novel techniques for exhausting the power from the plasma, where it hits the material surfaces within the machine at very high heat density, equivalent to what the space shuttle used to experience on re-entry. This is a very complicated part of the plasma to model. It is an exascale grand challenge, and it's a part of the problem that needs to be fully instrumented with the UQ to make sure that we don't burn holes through those components inside STEP. We need to validate the code that we're developing, though. This will be a 5 to 10 year program, and we've started off doing that by going for the simple problems first, by learning how to walk before we try to run. So we're actually working on very simple cavity-based fluid problems to start with. If we can't build the VVUQ around these and build actionable predictive capability for CFD, we don't stand much of a chance in being able to do it for plasma. So we're building a little test rig here on the right that will be able to confirm that by going to high order spectral HP methods, we can get an exascale scalable solution that can actually model turbulence properly. Now, the next challenge, though, is, as I said, at the moment, we tend to use our codes interpretively for exploring experiments. We need predictive capability, and this is where the black swans are going to become very important, the so-called unknown unknowns. These are very, very hard to predict. And they happen all of the time. So on the left here, you can see the discovery of high confinement mode, which happened in the 80s, I think, which of course is essential to the operation of ITER. This is where the plasma goes into a new mode of operation, where a transport barrier forms at the plasma edge. and the plasma confinement doubles. That's a good black swan that appeared. We also get bad black swans. So JET, in its early days of operation decades ago, underwent major vertical disruption events which weren't predicted. We understand disruptions a lot better now than we used to, but nevertheless, there might be other of these black swans that come out of the woodwork. Fluids, of course, are very, very complex state of matter. There's a lot of structure goes on inside fluids as there is in plasma. So there's a nice picture of Saturn's hexagon here, which is another black swan. We've got to get better at predicting the black swans. And unfortunately, the UQ methods themselves aren't particularly good in that respect, in that they tend to underpredict the uncertainty. So I'm nearly on my last slide now. So we've got to fix this going forwards and look for new UQ techniques. So the black swans tend to get affected due to the tails of the distributions. The variance and the mean aren't really good enough for predicting the failure modes of reactors. So we need new methods that are going to allow us to target these engineering problems a lot more effectively than the science problems that we're used to. And this means that we need to look for new methods that bound the exact risks properly. And as we do more statistics, we actually reduce the uncertainty estimations rather than see them start to increase. We need to address how inaccurate the UQ itself is. We need to work with very low data scenarios unless we get our own exascale machine for solving the fusion problems. And we need to work with imperfect probabilistic information. This is absolutely essential. A lot of the time, we don't know exactly how our UQ is playing out. We don't know how uncertain we are in many scenarios. And this is where we're starting to look at something called imprecise probability theory that I think could fit quite nicely into the CVIA project. So my last but one slide, the propensity of humans to introduce risk. Again, this is another where we see this all of the time. My friends in the engineering world, in the aerospace and automotive sector, see this all of the time. So Rolls-Royce did a study recently where they discovered that by putting engineers in a room with the same tools and giving them the same problem, they came up with wildly different answers. We see it all over the place. And in fact, we're all probably guilty of being George the data tamperer here on this little cartoon on the left. And the key to this, of course, is automation. And that's why we're exploring projects like the Omniverse program with NVIDIA. And also for the UQ itself. This is a little project that we've done as part of a European program through the European Open Science Cloud to try and make UQ more tractable to our engineers by building an easy front end for deploying UQ across the cloud. Lastly, I know I've run slightly over. I just thought I'd say a few words about why I've just presented this rather whistle-stop tour of the fusion problems in the UQ space. The reason really I've done this is because I think there are huge similarities between fusion and many other fields, not least pandemics. So if you think about it, if you look at a pandemic and you look at a fusion reactor, both are highly coupled, very complex system of systems problems. The models themselves contain significant epistemic uncertainty and, of course, aleatory uncertainty as well. Both suffer from a data validation problem and that we don't have an enormous data set to work with in terms of validating that the codes are truly predictive. And there's a data wrangling sharing problem as well. So I'm sure a lot of that has now been solved through the COVID-19 pandemic for the pandemic world, but it's still a problem for the fusion world. I think we all rely upon legacy codes and models. And, many of them are black boxes. And I think there we need to do better, but we still need to work with what is because, pandemics are going to continue to appear and we've got to get on and design step. And at the end of the day, the difficulty is around knowing how uncertain we both are about our different systems. So I think actually, from a computer science point of view, there's an awful lot of commonality. And so it's a very interesting question to ask around the UQ problems. Does it make sense to collaborate? And in fact, could a problem shared be a problem halved? if anybody in the room or listening in is keen to connect and talk to us about whether we could collaborate on the UQ problems, I'm more than keen to hear from you. Thank you very much. And I think I've got about 1 minute left for a question.
Yeah, thank you very much. It will be a short set of questions. Can we thank our speaker, please? Yes.
Thank you very much. I appreciate it. That was very good to see that you're linking with epidemiology. Another area of statistics that I wasn't sure whether you're involved in is advanced engineering design of experiments. Certainly looking at the tutorial on UQ this morning, it struck me that a lot of that was probably very closely related to design of experiments with complex surfaces. So personally, I think the international fusion community are pretty terrible at design of experiments. We've done test-based iterative engineering over the years, and we tend to build test rigs based upon a lot of tacit knowledge. You know, we've got a lot of gurus who take great pride in what they, know should be done next. I'm a big advocate of taking a data-centric engineering approach, and that includes around the designing of experiments and test facilities to validate our models. I firmly believe that every new facility ought to be designed specifically to validate our models and make our models actionable, rather than building these facilities as a sort of a field of dreams. So I think this is very much an area where we need to do better. I'm very keen to connect with people who understand similitude theory as well, to make sure that test rigs are specifically designed for validating models in the correct regime. And this, of course, is a very difficult problem for fusion, because really we need to be in the reactor regime to do the experiments properly and validate the models properly. We need a very large 14 MeV neutron flux to confirm that reactor components are actually going to work. So it's a real challenging area, trying to work out what you build next, given the amount of limited time and money, given the timescale we've got. But for that reason alone, I would argue that a design of experiments approach is absolutely key.
Thank you. I'm going to be very mean and stop questions now, so we don't run over time, but hopefully you can join us for the question and answer session later. And I can reassure you that even in epidemiology, we have a massive data issue. So it's definitely a common problem. Thank you very much. All right. We'll now welcome a real live speaker in the room and everything. Hopefully it will remain that way.